having Professor Chun, who is the Satish Dhawan chair, basically CHP. He is a versatile high-energy particle physicist and worked on various topics on dark matter, neutrinos, polar physics, and also superspectral phenomenology. He did his PhD from Seoul National University, and then was postdocs in DUM and ICTP and TIAS, and then he is a faculty member at TIAS since 2002. And he will be talking to us about Baryogenesis and Leptogenesis.
Okay. Okay, so welcome to the lecture. So happy to be here and give lectures on this, and also nice meeting you guys. Okay, so I don't know, the schedule can be flexible. So the original plan was to have 1.5 hour, 4 times 1.5 hour lectures, but it could be 2 hour times 3 or 2 hour times 4. So okay, let's see how it goes. So so for some references, I mean these days you can find a lot of references just by Googling. So some of the classic references I use is for cosmology, you know, Kolbe and Turner. The book by Kolbe and Turner. So what's the title? Title is The All Universe, right? And then for leptogenesis, what I like, I still, whenever I have questions, I go back to these two papers. So it has a title of pedestrians. I mean, I like this reference very much because I mean it is very clear presentation of conceptions. And then there was a more serious study by Judy Cheddar. In the title, it has the word complete. Seems that you don't have to look at any other papers. I mean, here, I mean, they included the thermal effect for the first time probably. And then usually, you know, so what I do is quite naive. So I usually don't take into account the thermal effect. I just, you know, use a simple Boltzmann equation. But whenever I need some complete result, I go back to this. And then check whether my naive calculation is okay or not, right? So, I mean, of course, if somebody wants to do more serious work, then this should be a good starting point. And then there are a bunch of review papers. Just by Googling lectures on leptogenesis, you can find a lot. Sort of one of the last review paper, probably very complete, is by Davidson and Neer and Nardi in 2008. The title is simple, Leptogenesis. So this means that, I mean, you know, this is a kind of complete review, including all the effect. And it's 2008, so you can realize that this topic is, I mean, is rather old. Now from 2008 on, and of course there are some progresses in some details, but basic feature remains the same. And then there are also, of course, variations of this leptogenesis. So I hope this lecture will be helpful when you try to extend this old idea of leptogenesis to other mechanisms. Okay, so usually I start this lecture with introducing some basic thermodynamic equations in the universe. So probably also good idea also here to repeat this, right? So anybody read Corbin-Turner?
I think it's a good idea because there are a lot of young students
Uh-huh.
who are not seeing this.
Okay. So yeah, I mean, yeah, let me just collect the formulae we need for our discussion. So so in the early universe, you know, the universe in thermal equilibrium state with a lot of thermal particles. So and then the important quantities we have to know is the number density, energy density, and the entropy and pressure kind of stuff. So let's start with equilibrium distribution of fermions bosons. Okay, so please interrupt me whenever you have some questions or doubts. You know, we have this equilibrium distribution function of fermions boson in terms as a function of momentum, which is and then here the energy as a function of momentum. In the simplest case, we have square root of momentum squared plus mass squared, right? And then in certain cases, in some complicated system, I mean, you know, dispersion relation can be different from this. But for our lecture, we will be only dealing with this usual dispersion relation. And then number density goes like integration of phase space and G is the degree of freedom, say left-right fermions and complex bosons. You know, in standard model, we have Higgs, which is complex, and left-hand right, the quarks and leptons. So you, I mean, in most of the time, you just take G equal to.
However, assuming there is no interaction, so that it is more like free particle dispersion energy.
Yeah, this is, yes, that's right.
So even if in the ideal universe density is high, there is no interaction when.
There are interactions here. We have standard model interactions, right?
Yeah.
Gauge interactions and Yukawa interactions.
I was wondering whether E will be modified.
That's right. There will be thermal correction, right? I mean, if some particle is in thermal soup, like a plasmon, we have thermal mass squared. Mass squared proportional to T squared. But usually, yeah, we forget about that in this calculation, and then which is good enough.
Can I ask a follow-up question? So we are supposed to do this calculation in an expanding universe.
That's right.
So this dispersion relation is not strictly valid there. So would there be curvature corrections as well? So because of expansion?
Oh, that I don't know.
But then it's radiation dominated, so it's still expanding.
It's still
Yeah, yeah.
Yeah. And so this dispersion relation is not valid.
No, this is related to co-moving schemes. Each schemes then is changing.
Huh?
Yeah, so you can do
Yes.
co-moving.
Yeah, you do it in the NBS.
Yeah, exactly. So that's a co-moving. But the A basically cancels out.
Right.
So you put away
So
A,
you
where is it?
So in local flat place, you mean?
No, I think we should cover that space. That's where we can move it. Yeah.
But energy is not conserved even there. Energy is not.
So that's the ratio value.
No, but we actually calculate the number density, we actually use some of the rules.
Yes. So that is the n by s. So energy is not conserved because of expansion we use. That is just a redshift value.
Okay.
So if you go to Pomori scale, then there is no expansion universe. Pomori scale is your liquid. So there the energy is.
Universe, even in addition to that, you may have all those fluctuations, quantum fluctuations, which will modify the entry constant. That will affect the your equation under, let's say,
So I think
secondary application.
I think
this is happening after that. This is happening after inflation.
And after inflation, and
Yeah.
these are 1 MeV.
Yes.
These 1 MeV starting point,
What is that one maybe?
temperature.
Oh, okay. So, I mean, for this, we assume the radiation domination error,
Right.
which is, I don't know, from 10 to 14 GeV, temperature of 10 to 14 GeV down to, I don't know, keV. Yeah. So, I mean, so through these interactions, we just assume every particles we are dealing with are thermal equilibrium. So, they follow equilibrium dynamics.
So maybe the question can be answered because you are in a regime where this thing is adiabatic.
Yeah, that's right, yeah.
So when the expansion is slow compared to some intrinsic scale in the problem.
Okay, that's good. Okay, thank you very much. Yeah, I think that's the right answer. Yeah, because as the universe expands, the temperature, it cools down. But this dynamics, okay, equilibration dynamics is very, very fast. So actually, yeah, we neglect this. Okay.
There is a good separation of scales and this.
Very good. Thank you very much. Yeah, I always forgetting about this. Okay, so yeah, really nice. I mean, please ask any questions, and then if somebody knows, please answer it too. I mean, again, this is a simple expression, and pressure. Okay, so and then another property really this chemical equilibrium condition. This is mu is a chemical potential, distinguishing the particle number and antiparticle number. For particle and its antiparticle. And then when some process in equilibrium, so chemical equilibration gives this kind of equation. So now in terms of, okay, so now given this, we can actually calculate. This function is rather complicated, so we may not be able to get a finite exact result. So we'll take two limits. One is the non-relativistic limit, and then the number density we get is, so in this case we can do integration of this taking, actually we can assume that the chemical potential and mass being 0, then you just integrate over 0 to infinity. So then you get this result. So fermion, there is a prefactor 3/4. And this is what zeta function, which is about 1.2. And energy density again for fermion is 7/8 and for boson is 1. And pressure so radiation or relativistic particles, the pressure is just 1/3 of energy, right?
So what was the argument? So how do we know that mu is much smaller than P?
We are just assuming that. Yeah.
That's an assumption.
Yeah, it's assumption. Yeah.
We
Yeah.
can't cross-verify this.
Yeah. I mean, in our usual standard cosmology, this is the case. And then, yeah, of course, you can have the case. For instance, condensed matter physics, mu can be as large as temperature, right? But we only deal with, in most cases, deal with this. Also, the mu is related to the baryon symmetry of the universe. Then mu is, mu over T is 10 to minus 10. So in standard cosmology, you never encounter the situation where mu can be sizable. I don't know, perhaps that's also interesting question. I mean, maybe there is some error of right after inflation, one may think of some exotic state having large mu, I don't know. Okay, so then and from that equation and the particle symmetry, the difference between particle and antiparticle is controlled by no pure mu. For fermion, boson is extra factor 2. I mean, okay, so the total, the average energy density is proportional to T cubed, and then so mu over T is the measure of the asymmetry. So as I said, for concerning our baryon symmetry, so mu over T is around 10 to minus 10. So in our system, yeah, we can always take mu very, very small. Also, of course, because of that, I neglected high order terms, right? There's contribution. You just expand, assuming mu over T very small, then you will get mu over T and mu squared over T squared and so on and so forth.
Sorry, maybe I missed how you got that equation from these.
No, you have to start with this. Okay, sorry. I mean, okay. Oh, yeah. This is really wrong. Actually, here I ignored. I mean, I put mu being 0 here, but you have to expand this. So you take a linear term of mu over T, then integrate out. Then you get this. T cubed, yeah. Okay, so dimension 3, so it should be mu times T squared. So this is non-relativistic for relativistic for the opposite limit. But usually, yeah, just okay, mu. And then again, in this limit, we'll be considering only this case. This is non-relativistic limit. So here, I mean, you can do this calculation numerically, but you cannot get finite. I mean, the exact functional form. So what we usually do is to take a Boltzmann approximation. Boltzmann. Does it have one n, two n? N, yeah. And then you do the integration again. Then what you will get is okay. So let me write down like this. Okay, so ignoring actually temperature, you can forget about then the energy density is nothing but number density time mass, right? In the non-relative limit. And then, okay, so in the linear, I mean, the leading correction could come from this. But yeah, for us, we this exact relation is not needed. Then pressure is n times temperature. And then this asymmetry quantity in this limit is just 2g. So although I write it as for completeness, we will be using this formula in most cases. So,
I have a naive question. Already because of CPT, would you not expect the number of particles and antiparticles to be the same? So therefore n and n bar will be, or is that not the right way to think about it?
yeah. But you know, but in our university, you know that CPT is broken. Sometimes.
CPT is good. When we see
Okay, CPT is good. C and CP. Okay, I mean now we have more baryons than actually we don't have antibaryon around us.
that
so-
is what we would like to explain, isn't it?
Yeah, that's right. That's the yeah.
If
So.
you start from a theory which is CPT good,
Mm-hmm.
then wouldn't we have equal number of particles? And
Yeah, that's right. If CPT is always good, CP is always good, then of course, yeah.
So then how is it that this elementary statistical mechanics can give us n minus n prime to be normal?
Okay, so we are assuming at some stage there is an input of generating non-vanishing mu. Yeah,
So the mu is different for the particle and the
yeah, that's right. And then we will see how we can.
shifted the mystery to why the mu becomes different.
That's right. Yeah. That's the whole purpose of this lecture.
Location of
Yeah, that's right. Okay, very good.
Basically, one of the Sapra's condition is to violate peak interaction. Basically, peak interaction has to be.
Yeah. Actually, okay, verification. Actually, I mean, since I said I am dealing with equilibrium thermodynamics, but there must be some stage where this is broken. So at some point, this is broken and generate mu. Then since then on again, thermal equilibration. Okay, so.
Sorry, can I ask somebody in the audience, so what is the status of CPT in an expanding pattern without Lorentz inversion?
Well, if you want to do strictly, if you want to do quantum field theory, then you don't have the notion of a particle. Then you have so then what you can do is just define states and algebras. I mean, you can define an algebra of quantum fields, and you can define states that carry representations. There, I think there is work that you can write. So there do exist states which obey the analog of state. But there are also states which don't obey analog of state, and you cannot choose one against the other. You cannot choose one or the other purely by introspection. You have to go and do experiments to see what the real world is. So purely theoretical work cannot tell you which side to take in an experiment. But there are states which are the analogues of CPT in gravity.
But strong gravity does not necessarily violate Lorentz invariance as well as CPT.
Yeah, to prove CPT you need Poincare symmetry. If you are in a situation where you don't have Poincare, then everything is up in the air.
When I may recall 20 years old paper by Alan Kostedeski, he also tried to propose some cyclicality interaction motivated by gravity. 2002-3.
You can make, the point is you can always create situations by hand. But the question, I think Aninda's question is, whether there is an intrinsic property.
Exactly. That's why I was saying gravity.
Okay, so discussion becomes very profound. Good. And then in this occasion, I'd like to mention, okay, it's okay. Yeah, so I'm also learning. And then, so there is also idea that Lorentz invariance or CPT is broken by the medium. So during the expansion, we have, the media itself has a CPT violation. Then it can be also a source of baryogenesis. So, yeah, medium has a violation of a CPT. So if you are living in the CPT violating background, then this can also a source of baryogenesis. So there's such an idea. But we are dealing with decent quantum field theory respecting CPT and Lorentz invariance. Then Sakharov condition and Sakharov condition should be met. So which is the main topic of this lecture. Okay. Okay, so so we can have total energy density. In radiation domination era, it's of course and G star is total number of degree of freedom for bosons and fermions. Okay, so this is summing over all the bosonic degrees, and this is summing over all the fermionic degrees. And then the standard model, so for temperature higher than electric symmetry breaking, which is around 100 GeV, then all the quarks and leptons, gauge bosons, Higgses are in equilibrium, so that you will get this G star around 100. G star S, okay, so G star S, okay, then good. Entropy, okay, then before that, so then from Friedman equation, we know that this total energy density of the universe should be same as this one, so it's a Newton constant. So the notation I like is this. So the Planck, this kind of definition of a Planck mass. So I'll use this so-called reduced Planck mass, which is 2.4 times 10 to 18 GeV, which is different from usual Planck. The other definition of Planck mass, which is 1.2 times 10 to 19 GeV. That's a good question. Can anybody? Why?
They don't have to be. You can make situations in the lab lab where you can easily make situations in the lab where they are there don't have to be. But if you are start off with a system which is fundamentally uncharged, and then you heat it, cool it, hit it, do whatever you like, then the chemical potential, because the system started off as a fundamentally zero charge system, the chemical potentials have to be equal. You can start off with a system which didn't have equal charge, and then the chemical potentials will not be. So,
Yeah,
somehow you want to create a situation in which local density fluctuations please correct me.
I mean, maybe my naive conception is the chemical potential is a measure of net particle number. Yeah, so I mean, so net particle number can be non-zero, but you can it can be zero if you have the same number of particles and the same number of antiparticles. So then the situation, starting from mu equal zero, you can create a lot of particle antiparticles. Still mu can be zero. So mu is the measure of net particle number, which is also a measure of asymmetry in this case. Okay. Okay, so now entropy density is this one. And then again, we neglect the contribution from number density proportional to mu, assuming they are very small. So then also, since we know all the rho and p relations, you can calculate it, and then so you will get so in principle these two quantities are different, but that in standard cosmology that difference came only after E plus E minus annihilation down to 0.5 MeV. So I mean, for the details, you may go some references. So in our case, we don't distinguish between them. So this entropy density, the total entropy is conserved. So it's very useful. Here, okay. So Hubble parameter, where did I write? Yeah, of course, Hubble parameter is the expansion rate of the universe. A is the scale factor, and since total entropy is conserved, of course this is T dependent. So this quantity should remain constant. So it is quite useful for us to define so-called Y number. So once you produce certain particle n, particle number density n, then this ratio should remain constant through the history of the universe. So we'll be using this y is our quantity, and then in terms of this notation, baryon asymmetry measured is about, so there's a constant number we'll be deriving finally in our lecture. And then asymmetry say y delta n. So this should remain also constant, which is say so up to some constant factor, so mu over t is the y number of the asymmetry.
Eventually gives rise to 0.8 over minus 10.
Mm-hmm.
I mean, there are many variables. Observation 2 minus 10 is the asymmetry part entropy.
That's right.
But okay, you are saying if this is to be reproduced by theory, then you are searching for mu by
t. Yes. Yeah. Okay, so from observation we know that number. Then at some stage in the early universe, at some finite temperature, there may be some process producing mu by t of that number. So yeah, that's the final goal. This is kind of, yeah. Also in the literature, people use delta b or b. Okay, so you have to understand. When talking about asymmetry, this must be b minus b bar. And sometimes just write b as an asymmetry. Yeah. Okay, so now from this, actually we know the Hubble parameter in the radiation domination era. So Hubble parameter is which is about 3.4, taking G star around 100. And then at present, the critical density of the universe is measured by Hubble expansion today. And then H0 is measured to be small h is defined like this. And then we know that the h should be around 0.3. So now the present expansion rate is say 70 kilometer per megaparsec. In unit of giga-year, the H naught is about 14 giga-year, which is the, roughly the age of the universe. This Hubble parameter is measured by CMB measurement. Also, in the current universe, we know how redshift, the distant stars redshift, supernova, and so on and so forth. So from there, so we can also measure H naught. They give somehow different result. So this is so-called Hubble tension. So from CMB measurement, H is around 0.6768 kind of, and then from this local measurement, what you get is 0.7273. So this is still a problem. Some may take it seriously, some may not. So I am taking the second position. So H, okay, so we'll be using H to be 0.7. Okay, of course, you can choose whatever you like. Okay, so then from that we can get the critical density of the universe, which is concerning, considering uncertainty. Is this H squared? Why H squared? Uncertainty in little h, we just keep it. In particle physicist notation, we like energy unit so much. So in terms of GeV per cubic meters, critical energy density 10.5, which means that there may be about 10 protons, neutrons in cubic meter, right? And then measured energy content. So we define the omega, which is a ratio of some specific energy density divided by critical density. So omega b, then considering uncertainty in H, okay, so yes. Okay. Basically from the CMB anisotropy measurement, we know this quantity really precisely. So here I take H to be, H 0.7, so H squared is about half. And then energy density, the vacuum energy density is about 73%. Okay, so now since the reason why I'm talking about this is that I want to calculate YB. So So after Big Bang nucleosynthesis, we produce this much matter in our universe. So that means the baryon number density. Well, in this case, this can be baryon or antibaryon. I mean, now we have only baryons, right? So this is really baryon number density. It's defined by NB over S at any temperature. Now we calculate this in terms of the present day number. So then from this so MB is baryon mass, I mean nuclear mass, right? Which is around 940 GeV for proton or neutron, and rho B we know. So rho B is omega B rho C MB over S 0. From this, what do you get? And then S0 we know also from, okay, so the temperature of CMB now is about 2.7 Kelvin in terms of our beloved unit. This is about 0.2 milli-electron volt. And then entropy density, I mean, we got the entropy density relation 2 pi squared over 45 G star T cubed. So then you can calculate, so entropy density now is about 2,900 per cubic centimeter. So now, yeah, I mean, you can get this number from this, which is, yeah, of course, taking baryon mass about 940 MeV. So this is the number of baryons in our universe. Then we say, oh, that's the asymmetry we should get. But why? Why should there be asymmetry? Yeah, that is the. I mean, we want to understand this question. Okay, so to proceed. We'll talking about freeze out of some particles. So we are dealing with thermal equilibration quantities, but at certain point, some particle can get can decouple from thermal soup, meaning that their number density will remain constant from some temperature. So this is called the freeze-out process. So this happens, I mean, this freeze-out number density will depend on the interaction rate and the expansion rate. So we'll see how it works briefly. So Okay. So let's consider the number density of a particle in thermal equilibrium. So from the previous equations, when temperature is much higher than the mass, what we got is this ratio to be, for fermions, we have extra factor 3/4, and the degree of freedom of a particle, and then total relativistic degree of freedom. And then this number is what? Let me see. It's about 10 to minus 2 or 10 to minus 3 at very high temperature. And then in the non-relativistic limit, if you remember the previous expressions again, of course this must be G star S, but again, as I said, we don't distinguish between G star and G star S. At low temperature below the mass, so we'll have a Boltzmann suppression. So this is the equilibrium Y number. So as a function of m over t, I can draw Y number like this. So at very high temperature, this Y number is about 10 to minus 2. And then at low temperature, we'll have this exponential suppression. Now, if everything is in thermal equilibrium, I mean, okay, so if some particle's interaction is very, very strong, it's very strongly interacting with thermal soup, they will remain in thermal equilibrium longer and longer. So it will follow this equilibrium distribution. But at certain point, this interaction can be decouple. So it may freeze out. The Y number can maybe freeze out at high temperature. So this is okay. So let me define this parameter as X. So this is called the freeze out point. Or if its interaction is very weak, then it may decouple earlier time as well, when they are still relativistic. So then their final Y number should be around 10 to minus 2. So we'll see how this happens. So this 1 hour. You want to take a rest, or can we go on for another 30 minutes? And
I have one question. Why do you particularly require early reverse physics? I require potential imbalance. I require some adequate temperature. Now, in this universe, also a lot of black holes are there, viscous flows are there, which definitely violate energy. I mean, conservational energy is violated. What precisely early universe physics brings in? So that has to be in early universe itself. Why today's universe cannot be this?
Sorry, I don't get the question properly. So why we are dealing with the thermal property of the early universe? That was the question.
See, the ingredients, as I understand so far,
Okay.
you have introduced to accurate observed baryogenesis, baryon asymmetry.
Okay.
Basically, our chemical potential imbalance
Uh-huh.
and temperature.
Okay.
Now, of course, Safran's conditions are there to be satisfied, etc.
Okay.
But other language, the three Safran's conditions, why cannot be satisfied in today's universe as well? Today, black holes are there, primordial supermassive, where conservation of energy is violated for particles. So why I have to depend on early universe physics to get the
Okay.
Are you asking why baryogenesis is not happening now?
yes today?
Okay, good question.
Another
Okay, I mean, we know, okay, so there are two milestones of Big Bang cosmology. One is BBN, the other is CMB. So this we know very precisely, I mean, from the measurement, also from the the theory, right? Actually, thermodynamics and particle physics in weak interactions determine how BBN occurs, how elements, protons, neutron, helium, light elements are produced. So we know, I mean, this is through this thermodynamics. Now, at the time of BBN, there must be only baryons, not antibaryons. So already at BBN, around 1 MB of temperature, there are this number of baryons in the universe. So the baryogenesis should occur before BBN, not now. Okay?
Because otherwise they will collide with each other and annihilate. Nothing will form.
So, I mean, maybe a related question. What is the earliest evidence that we have where there was asymmetry?
MEB.
That is BB.
MEB, before MEB. If you produce symmetry before MEB, it's okay.
So that's the BB.
Yeah.
So that because
Yeah.
that happened such a long
So, yeah.
And I think that there might be another.
And then actually we will see, I mean, probably, I mean, I will get to that point by having this calculation further. So we will, okay, so the short answer is that if you have some asymmetric universe, same number of baryons, antibaryons, then there is strong interaction. Baryon, antibaryon annihilate into two pions. Okay? Proton, neutron, p bar should annihilate into two pions, and pion decay away. So this cross-section interaction rate is so huge. So it will gonna reduce the symmetric component. The corresponding symmetric component, the corresponding Y number of symmetric component is 10 to minus 20 something. So if we assume symmetric universe, same number of baryons and antibaryons until the era of BBN, then there are no baryons to form, our materials, our metal. So this, I mean, as an interesting fun exercise, we'll be calculating how the freeze-out process will reduce the total number of baryon and antibaryon so drastically. Then the result we should get is that there must be a symmetry before BBN. There must be a symmetry of 10 to minus 10 before BBN. Otherwise, we would get only baryon number 10 to minus 20 something. So it's a spoiler. Okay, so I mean the story goes like this. Okay, it's clear.
Maybe there's another related point, which is that as far as I know, the baryon asymmetry is uniform throughout the observable universe.
Yes.
You find only whereas if there were objects like black holes that created baryon
Okay, I see.
then you would find baryon asymmetry more near the location.
Okay, good. Yes.
To the best of our knowledge, baryon asymmetry is uniform across the entire observed universe.
Yeah, basically, the universe is isotropic, so.
So in that sense, black holes are also abundant throughout the universe.
Yeah, but we don't, I mean, but the baryons are are much more
That
abundant.
is why actually I asked the question. Some people
Okay, so uniformly distributed black holes producing baryons. Okay, yeah. If, for instance, if there is one black hole in each galaxies, that may be okay. And but by the way, why are you talking about this black hole producing baryon symmetry? Is there some?
No, I didn't say that. He said that.
I mean, is there some model producing baryon symmetry from black hole? It could be interesting.
Some paper, few,
I see.
years, 20
Okay.
years, 50 years back maybe. But yeah, one caveat is there. If black hole indeed produces baryogenesis, then there is no guarantee that. I mean, there are also rotating counterclockwise, also clockwise.
Okay.
They may cancel out.
Okay.
Also,
Okay.
equal and opposite asymmetry will be cancelled. So I was just basically thinking
Okay,
of those
okay.
some other paper.
Okay, I see. I mean, also in this case, the primary black holes would be there, and then they may be a source of baryon symmetry as well. I don't know. Okay, so I mean, so at the end of this explanation, we'll see how baryon and antibaryon number can be reduced through this preserve process. Also, this is basically the calculation why CDM, so-called weakly interacting massive particle, can be a good dark matter candidate. So, yeah, let's go on, and then probably we can finish in 30 minutes this part. Okay, good. So we are talking about only equilibrium dynamics, but at a certain point, there must occur decoupling of a particle from the thermal bath. You know, from BBN calculation, we know how much, how many baryons, antibaryons, okay, electrons, and so on. So actually, all the calculation follows this kind of mechanism. So for instance, let's consider some particle X annihilating to some lighter particles, or the forward process or backward process at high temperature can be in equilibrium. So you know then the number density energy of them just follow the quantities we just described. But as temperature becomes lower, the total, if they are in thermal equilibrium, number density is reduced. So number density reduced. So this particle, there is less chance for this particle to meet each other. So the interaction rate can get smaller. So measure of decoupling is the interaction rate smaller than expansion rate. Now, of course, this is the Hubble parameter, which is inversely proportional to the age of the universe. And then interaction rate, let's say gamma, then this will define the time unit of interaction time unit. So that means if the typical time scale of interaction is much larger than Hubble parameter, age of universe, then this cannot happen. So then number density freezes out. So gamma is basically defined by number density, particles colliding each other, and then cross section. So So when they are relativistic, NEQ goes like a T cubed. When non-relativistic, it has a Boltzmann suppression. So when relativistic, this is T cubed, and then cross section is 1 over mass squared. So it has a mass dimension 1. It also has a mass dimension 1. Okay, I mean, if you set a Boltzmann equation and then try to solve it, actually, yeah, this quantity will appear somewhere. So this is, it's very naive calculation, but still very good. So you can rely on, for any process, you can make a rough estimate from this calculation. Of course, for detailed, more precise determination of final freeze-out number density, you have to solve Boltzmann equation. But for our purpose, okay, so this is velocity, the relative velocity. And then this means that thermal averaging. So we are having thermal equilibration. So, I mean, this has done with integration of a thermal background. But usually, I will assume that the sigma v is constant. The cross section, annihilation cross section goes like 1 over m squared, m being the mass of colliding particles, right? So I will assume that this is constant when they decouple when relativistic, but it may have also temperature dependent. So real calculation can be more complicated, but for simplicity, I will assume that this is a constant quantity. Then we will see what will happen. And then in most cases, actually, yeah, in most particle physics model, sigma v is constant. So freeze out occurs when from this you can calculate the so-called freeze out temperature. So relativistic case, meaning XF much smaller than 1. So basically some interaction is so weak, so this particle can, number can never be surpassed by Boltzmann factor. So then in this case, I mean, this final expression is quite straightforward. So YF, the freeze out number density, is just constant, right? Which is given by this number, 10 to minus 2. Then, okay, so this is called a relativistic remnant of the early universe. So their number density will remain same till now. So their content in our universe so let's say, what is this particle? Some particle X, yeah, and freeze out can be calculated as this is a constant number density normalized by entropy density, and then this is the mass. So m times y is the number density at present. And then now we multiply the entropy density of the current universe. Then this is a number density at present, right? Then divided by rho c. So then you will get the usual factor. So if some particle decouple, when they are decoupled relativistic, then their mass should be smaller than, now, you know, this quantity, so there is h squared somewhere. Now you know that at present the relativistic degrees are just photon and neutrino, and then matter is non-relativistic and ordinary matter, and then dark matter must be non-relativistic, should be cold. So this component should be, you know, cannot be that large. Probably we can accept 1% of them. So that means if there is such a species, then the mass should be smaller than what? About 10 electron volt or so. Actually, in older days, when we didn't know about neutral mass, so neutral mass around factor 10 electron volt could be a dark matter candidate, and then no, it is not cold; it's hot. So because these days, this possibility of dark matter is excluded. But anyway, yeah. So this is a possibility. And then more interesting is the so-called non-relativistic decoupling. No. So freeze out occurs low temperature compared to the mass. So again, as I said, we will assume that sigma v is constant. Then the freeze out number density should be like no, here it is. So here we can just put freeze out temperature. Then you can determine, given the value of annihilation cross section, you can equate these two quantities to determine XF. So there is left-hand side is this times cross-section, and right-hand side is Hubble parameter. Then if you know this number, then actually you can calculate freeze-out temperature. And then it will be an interesting exercise for you to follow this. You know, whenever you want to have some cold dark matter candidate, of course, you can solve Boltzmann equation directly, but you can quickly get an answer from this calculation. And then omega x, so let's have this expression. Okay, so then finally, let me just write the answer directly. Okay, so if I take annihilation cross section to be 2 times 10 to minus 9 inverse GB squared, you get freeze out temperature, freeze out number 25. From this calculation, you can check it. Taking this nominal number of G star and G, then you get the CDM fraction, which is measured. So 2 times 10 to minus 9 GB minus 2 is typical weak scale cross section. This weak interaction GF is what? It's about 10 to minus 5, right? And then there are phase factor over 4 pi, coupling constant somewhere. Then you can easily get this nominal annihilation cross-section in the early universe. So that was why the supersymmetric neutral particles in supersymmetry can be a good dark matter candidate. They have a natural weak interaction of this size. So Higgsino, neutral Higgsino or Portino can be a good dark matter candidate. So this is called the WIMP. And people say this is a WIMP miracle. So whenever you have weakly interacting massive particles, so it can, and then stable, neutral, is automatic dark matter candidate. Now, our final goal is to calculate the baryon, anti-baryon freeze-out density. Now everything is straightforward. For nucleons, proton and neutron. So PP bar going to pi 0, or pi plus pi minus, P and bar going to pi plus pi 0, and so on and so forth. The cross section, we know. I mean, we know this. So nucleon cross section. So then you should be able to calculate annihilation cross section from this diagram, right? So instead of doing this fancy calculation, it's not so fancy, elementary calculation. So as a naive approach, gamma 5 is pseudo scalar. And then of course GA, I didn't write it somewhere. GA, I don't know. So, the one number. Okay, so we will be very naive to take this is just a classical cross section. So what is radius of a proton? I don't know exact number, but should be around 1 femtometer. So then you can immediately get this cross section to be 80 GeV minus 2 in terms of GeV unit. By the way, you know this natural unit for particle physicist? So in this unit, 0.2 GeV times femtometer is 1. Okay, so if you do the calculation precisely, then there will be the factor of 10 or 20 something difference in this calculation, but we don't care about that. So yeah, let's just use this as a cross section. So you know this is much larger than the usual CDM nominal CDM annihilation cross section. So I mean you can follow the same calculation as I described before. So now you take 80 inverse GeV squared. Then if you calculate solution of this, then you will get freeze out temperature 50. So meaning, I mean, okay, if cold dark matter should have frozen at this 25, then baryon should be freeze out at even lower temperature. So meaning that there is a further suppression of the final number density, right? So as a result of this, what you get?
You would also want to change the omega to omega b.
Omega.
The left-hand side.
Oh, sure, yes. And then, okay, in this case, this is omega b plus b bar, same. So we start with, yeah.
Because the previous one was for the cold.
Yeah, good. So what you get? Is okay. I mean, you can still use this. You just take this 80, this is 50, then you will get (10⁻12). But the measured value is this one. Which corresponds to YB around 10⁻10. I mean, as I said, so already BBN time, you should have this amount of baryons in the universe. So if you just assume symmetric universe until baryogenesis temperature, yeah, the material we can use is way too small. So that means what? So there must be some anti-symmetry, asymmetry. There must, I mean, if there is asymmetry between baryon, antibaryon around 10⁻10 before so this amount cannot be annihilated away, right? So the baryon we observe today should come from the asymmetry. So now, I mean, okay, so this is the question of baryogenesis. So then, what are you gonna do? Okay, so simple prescription. So after Big Bang, you just put this asymmetry. It's God given. Then, you know, physics is not interesting. I mean, so there is, we have to lose our job. And then, of course, you know, it sounds like it's a reasonable assumption that the universe was symmetric. But if there is a way to generate this asymmetry dynamically, so probably that's the right path we should take. So then there came the Sakharov to say that from the symmetric universe, we can achieve a symmetry if certain conditions are met. So we'll, instead of, probably this is good point to stop, and then let's continue next time. Okay, so questions? So I'll be sitting in the Rohini's office, so please come to me whenever you have some questions.
Okay, so we stop for today, then we'll go next week.
Okay.
Next week.